Welcome to The Explainer. Have you ever just stopped and wondered, what does the universe's fundamental rulebook actually look like? Well, today we're going to try and figure that out. We're going to build our reality from the ground up, starting with the very smallest things we know exist.
It is a massive question, isn't it? But here's the amazing part. Physics tells us that a few really elegant rules, just a handful of core principles, govern absolutely everything, from the quarks buzzing inside a proton to the colossal dance of entire galaxies. So let's just dive right in.
To understand the rules of any game, you first have to meet the players. And for us, that means we have to shrink ourselves down, way down, to a scale that's honestly almost impossible to wrap your head around. The world of fundamental particles.
And this is it. This chart here, the standard model of particle physics, is basically the complete cast list for our entire universe. Now, don't get intimidated by all the symbols. The big idea, the main takeaway, is that every single thing you see, you, me, the stars, the device you're watching this on, is made from combinations of these few particles. I mean, think about that. It's just an incredible achievement of science to have boiled everything down to this.
So these particles are kind of organized into two main families. On one side, you've got the quarks. Think of them as the social ones. They feel what's called the strong nuclear force, which is like this super powerful glue that holds them together to build bigger things, like the protons and neutrons inside an atom. And then on the other side, you've got the leptons, like the electron. They're a bit more independent. They're the loners, they don't feel that strong force, so they're perfectly happy to just exist by themselves.
Okay, so we have our building blocks. But a pile of Legos isn't a spaceship until you have instructions and a way to connect them. For our particles, that rulebook, that connection, comes in the form of forces and the fields that carry them.
And here's where you start to see this beautiful symmetry in physics. Look at the math for gravity between two masses and the electric force between two charges. It's the exact same pattern. It's called an inverse square law, which is a fancy way of saying the force gets weaker with the square of the distance. It's one of nature's most elegant little tricks, just reusing the same rule for totally different things.
And these fields do a lot more than just push and pull. They're basically huge reservoirs of energy. That curve on the right, that shows the energy locked inside atomic nuclei. When we fuse light elements together, like what happens in the sun, we move up the curve and release an enormous amount of energy. And when we split really heavy elements, like uranium, we move down the curve from the other side and also release a ton of energy. That's the power locked away inside these fundamental forces.
All right, we've been deep in the weeds of the quantum world. Let's zoom out now and see how these tiny, invisible rules build up to create the motion we actually see and experience all around us every single day.
These three ideas are basically the language of motion. It all connects back. A force, which we now know comes from those fundamental fields, causes a change in an object's momentum, its amount of motion. And to do that, you need a transfer of energy. See? It all loops back together.
Of course, things don't always move in a straight line. Anytime you see something turning, whether it's a planet orbiting the sun or a car going around a corner, there has to be some kind of net force pulling it towards the center of that turn. We call that centripetal force. Now, the key thing to get is that this isn't some new magical force. It's just the result of other forces, like gravity or friction, doing the work.
And this is just a brilliant example. As this car drives over the curved bridge, gravity is pulling it down. But part of that gravitational force is being used as the centripetal force to keep the car on that curved path. If the car goes too fast, gravity just isn't strong enough to provide all the centripetal force it needs, and whoop, the wheels actually lift off the road. It's a perfect little balancing act between speed and gravity.
And these rules of motion don't just apply to things you can see, like cars. They also govern the invisible world of electricity. These graphs show a capacitor, which is just a little component that stores electric charge. The motion of that charge as it fills up and drains out isn't chaotic at all. It follows these beautiful, predictable curves. It's just another example of these reliable rules in action.
So we've gone from the tiniest quark all the way up to a car on a bridge. Now, let's take these very same rules and apply them to the biggest stage we can possibly imagine, the entire universe.
And this is the part that is just so mind-blowing. The equations you see on this page, the ones describing the cosmos, they're built from the exact same principles we've been talking about. The gravity that holds a car to a bridge is the very same gravity that holds a galaxy together. The physics is universal. So in the early 1900s, an astronomer named Edwin Hubble pointed his telescope at far-off galaxies. He was expecting to find a random mix, right? Some moving towards us, some moving away. But what he actually found, well, it was staggering, and it changed everything we thought we knew about the universe.
He discovered that almost every single galaxy is rushing away from us. And even weirder, the farther away a galaxy is, the faster it's moving away. This could only mean one thing. The very fabric of space itself is stretching, carrying all the galaxies along for the ride, kind of like raisins in an expanding loaf of bread.
You'd think, okay, great, we've got it figured out, right? This whole story, from the standard model of particles all the way to the expanding universe, it seems so incredibly complete. But the more we look, the more we realize our rulebook might have some pretty major chapters missing.
See, when we measure how fast galaxies are spinning, there's just not enough visible stuff. Stars, gas, dust, to provide the gravity needed to hold them together. They should fly apart. So there must be some invisible stuff we call dark matter. And then, when we measure the universe's expansion, we find out it's not slowing down like you'd expect. It's actually speeding up, being pushed apart by some mysterious dark energy. Get this, those two things, they make up 95% of the universe. So the ultimate question physics leaves us with is, what is this other 95%, and what new rules will it reveal about our reality?